All right, today's question is, would you please define and explain what each lines of this graph represents, each of the lines? We're talking about this graph, even though it's already a smooth one, so I guess it would be more helpful to examine the source, this one, all right? So, what do we see here is the solar polar fields. And what are these exactly? Well, let's go to the website, see what they say. So essentially, we're observing like the uppermost, what is it, 25 degrees of the sun. So we look at the sun and we look at the top 25 degrees in terms of latitude, okay? So 25 the furthest from the equator, or 25 the closest to the pole, if you wish. To the pole as we see it from Earth, that is. And I'm going to explain that a little bit later. What's the difference? So we look at the north and we graph like how strong is the field in the north, okay? And this is what we, all right, maybe this graph is more helpful actually. So we look at the north and we see this blue line. It's the polar field north, you see. So when it's maximum, so what does it mean? It means we're counting when we're looking at the sun, and we use like magnetic whatever data. I mean, we look at the sun optically, but we like imply the magnetic field somehow through some methods. I don't know. I'm not a heliophysicist. And we're counting essentially how many field lines exit the sun. Okay, so this is the definition of the north polarities, the lines of field lines exiting the sun. And I repeat, we only observe the top 25 degrees. And this is represented by this blue line, all right? So when there's a lot of north polarity lines exiting the North Pole, we have the maximum of the north polarity, which happened around October 3rd, 2019, or something like that. October 2019, maybe September actually. Uh, this corresponds to, I guess, somewhere here. Wait, might be completely delusional. Maybe somewhere here, actually. I don't know. No, let's look at this one. It's easier to analyze. Yeah. So when we see almost no lines of force, magnetic field lines, exiting here in this section, right? We observe zero. We say it's the blue line is at zero then, which last time, actually it's like kind of happening right now, but before that, the last time it was 2013, 2012, something like that. All right, and vice versa, like when the blue line is here, it means the lines of force are exiting here from the south, right? Likewise, we observe like the bottommost 25 degrees in terms of latitude. And if the field lines exit there, then we say, okay, the north polarity is sort of in the negative. It's like, it's magnetic north, but it's now in the south. Okay, so the lines of force exit from the south, and there's a lot of them, so we have a maximum in terms of, like, the number. It's negative, but the number is big. Okay, and we again rewind the time backwards. We arrive at this point where in the south, basically no field lines were exiting the sun. And vice versa, the red line, it's showing where the lines enter the sun, or rather how many lines enter the sun in these polar areas. If a lot of lines enter the sun in the south, we get this, right? The red is highly negative, so to speak. When there's basically no lines exiting the sun, entering the sun, I'm sorry, in the south, we get zero of the red line. And when there's a lot of lines entering the sun in the north, we get positive red line, if that makes sense. So, long story short, this picture, when blue is very positive, red is very negative, it means the sun is basically like a dipole. So the lines exit the north, enter the south, okay? When we're at zero, it means that the poles are kind of empty of fields, both of poles. So all the magnetic field lines like are exiting and entering somewhere near the equator. on either side of the sun. I mean, obviously it rotates, etc., but it doesn't interest us very much. And vice versa, when you have highly negative north, highly positive south, it means the lines are exiting south and entering north, which is the opposite polarity to this cycle, for example. Actually, like, we're gonna observe that, like, the next minimum would be exactly that. The north will migrate to the south, and the lines would start exiting from the south in the next minimum and entering in the north. That's what will happen in the next minimum. There's a parameter called A, I think, like capital A, and when it's positive, like, the lines exit north and enter south. So heliographic poles and magnetic poles are of the same, polarity, you might say. And when A is negative, it's vice versa. So we're exiting positive A phase, where we've peaked in 2019 roughly, during the last minimum, and we're entering the negative A phase during the next minimum in 2029, something like that, 2030 maybe. Yeah. All right, so let's look at the original still, because you can see there's some interesting stuff going on. Like, why is it oscillating like crazy? Well, it's actually because, so, okay, let's re-examine. These are smooth graphs, okay? What do I mean by smooth? Well, they're filtered by 20 nanohertz, and they're saying the same here. Wait, let me see it. 20 nanohertz low pass filter. What does that mean? What is 20 nanohertz? Well, it's roughly once every 1.5 years, something like that. So we kind of ignore short scale oscillations and we kind of smooth it out temporally, okay? And once every 1.5 years allows us to get rid of this yearly oscillation. So this oscillation is due to Earth's orbit, because these guys are looking at the sun from Earth. And the Earth's orbit is, like, imagine this is the solar equator. It's actually not, because this picture is also taken from Earth. But imagine it is. And our orbit is tilted with respect to the solar equator. So in spring, we're actually up above the solar equator. So we see the north really well. We see, like, this kind of section of the sun, with a lot of north poles being visible and not a lot of south pole being visible. And half a year later, in September, we're below the solar equator, so we see a lot of south pole. I'm sorry, it's vice versa actually. No, it's correct. Yeah. In September, we see a lot of south pole and not a lot of north pole. That's why in September, like, the southern pole would be artificially stronger, if you wish, like stronger than it should have been in our observations. So you can see, like, the last peak this autumn, right? September, October. So the south was peaking and the north was falling, right? I mean, it should be vice versa. Actually, I don't really remember, to be honest. Wait, let me think about it. No, in September we're here. Yes, in September we're up above the equator. Never mind. In September we should see stronger fields in the north. And in March we should see the southern pole. Yeah. So this one was September. So, well, whatever was happening here, this peak is caused by it, okay? And the same thing goes on every year. So if you filter this with a 1.5 year period, essentially, you get rid of this oscillation, more or less. I mean, of course, like, some traces of it remains, as you can see here. But you get this smooth curve. Okay, so this is the smooth curve. Or rather, look, this black one. So these are individual north and south, just as we've discussed at the beginning, the blue and the red. But they've taken in... well, it's kind of out of phase with respect to this one. You can see that here they're, like, inverted, and here they're in the same sense. So it's just the strength, right? But nevertheless, what I was saying is that this black line, which also oscillates, is the average. You can see it. So we take north value minus south value, and we divide it by 2. We get this oscillating part, but which is kind of signless now, if you know what I mean. It just indicates the asymmetry, if you wish. And at the same time, it indicates kind of the absolute value of the field overall, of the overall field, if you wish. And if you smooth it with this filter of 20 nanohertz, you get this sort of more calm curve, right? And this is what they're showing here. They're only showing the averaged curves. Here we have only one averaged curve, not averaged but filtered, like smoothed out. There's only one curve smoothed out, and here they artificially take the numerical data from this website. You can see it here. And they take the average of the south, the average of the north, and the average of their difference. You see north minus south, which indicates kind of the field strength overall, plus the polarity, all right? So here we have north in the north, south in the south. Here we had vice versa, so that's why it's negative, right? The black line. All right, hopefully that explains something. I know it was a bit confusing, and I was confused during this when I was trying to explain the Earth's orbit. But eventually I got it right, I think. In autumn, in September, we're above the solar equator, so we see more of the North Pole. That's why here more lines would be like visible, you know, exiting or entering the polar area proper. That's why we get this weird oscillation with 1 year period. And in March, April, we're like below the equator, so we see more of the South Pole. And so it's also going to be like distorted, north versus south, like it would get a boost in its asymmetry, whereas it shouldn't have. So if you get this filter, you get rid of this oscillation. So this data is not very reliable in this sense, right? It's kind of skewed a little bit, but if you look at it, at the bigger picture, you can see what's going on. So the field reversal, when the poles are basically the entering or exiting lines are absent at the poles, these are basically the solar maximums. And as you can see here, we're right in the middle of one right now. All right.